To see, I want us to try to see how to do secret voting. So we have 4 of us, we have 5 of us here. I want us to try and see how we can implement the knowledge of divisibility on secret voting. That is where we are supposing there's a committee, and this committee supposing want to vote on an issue, and we want this voting to be secret so that nobody knows how you voted. How can we implement this using divisibility? Is that okay? So that's what I want us to try. And so what we shall do, since we are 5 of us who are present, I'll give each of you a piece of paper. Then I'll first of all I'll write some number, a secret number, on a piece of paper, and then I give to the first person. Or if that is not a vote, so that's just my secret number. So once I give that piece of paper on to the first person, what the first person will do, if we are voting for maybe a budget, want to pass a budget or fail it, is that okay? So what you're supposed to do, once you get the piece of paper, we are 5 of us. You write 6. If you want to pass the bill, if you want to pass this budget, you add 6 to the number you will get. And if you wanted to fail it, you add a 1. Is that okay? And if you don't want to either vote yes or no, you add a 0 to the number you will get. Is that okay? Then I'm the one who will vote last. So I want us to do it so that it's secretive. So I'll write a number. Supposing I write 50, then I give 50 to him. I'm not saying the number I'll write, it just be secretive. So when I give that 50 to him, the first person, you decide whether you want to pass the bill or you want to fail it. If you want to pass it, you add a 6 to the number I give you. The total you get, you give to the next person. Is that okay? You return my piece of paper. You return my piece of paper. I give you my piece of paper with a number. You are either adding 6 or adding 1 or adding 0, depending on the decision you're making. So if you are passing the bill, if you are voting yes, you add a 6 to the number you get. If you are voting no, you add a 1. So I don't know what you will vote, but it's you yourself, you know, is that okay? If you decide that I not vote, you add a 0. The number you get, you give the next person. So the next person will not know what you voted, because you are either voting, you are either adding a 6 or a 0 or a 1. Is that okay? So the next person will not know what you added because you returned my paper. And then after you forward your paper to the next person has an option also to add either 6 or a 1 or a 0. Then returns your paper and forwards his result to the next person. I don't know whether you understood. Yes, so this is your piece of paper. Then this is yours. That is yours. And forward this one. That's assisting your friend. Assisting the friend. And just in the voting. Just in the voting. It's secret voting, so I'll just explain again. What we are doing is I write a secret number. Then that secret number, I give the person number 1. Person number 1 decides what to do. whether to vote yes or vote no. So we are imagining we are a committee and we are voting for some budget. So the members will decide whether they want the budget to pass or to fail. Is that okay? So once I write this secret number, I give the first person. The first person cast his vote by either adding a 6 or a 1 or a 0, where 6 means he's voting yes. 1 means he's voting no. 0 means he's voting, is abstaining. Then after that, his total. Now the piece of paper I've put, you just write the total. You just write the total and then pass that total to the next person. Is that okay? So the next person also decides what he wants to vote, whether yes, no, or abstain. Then returns your piece of paper and forwards his total, only his total, to the next person. The next person also decides what he wants to vote, returns your paper and forwards the total. Then I leave the last person to vote. So what I want us to then, at the end of the day, you want to find out what that voting is secretive. Is that okay? That's what I want to achieve. So I want to just write my secret number. So I pass to the next person so that we make sure that that secret number, nobody sees it. You pass the total. So you just add your total, then you pass the total to the next person, and you return my piece of paper. So that total, you do it off head so that nobody can tell what you voted. You pass the total, your total to the next person. The next person votes, returns yours, and passes his total to the next person. Now, once the last person votes, you give me so that I also cast my vote. Just estimate your pen. Yes, this here. Here is your pen. Okay, so the voting has entered. So I want to see whether that voting was secretive. It was secretive because when I gave my first paper with the secret number, the only person who knew the secret number was the first person. The first person casted his vote. The second person was given the total of the first person. The second person doesn't know what my secret number was. Is that okay? He doesn't know what my secret number was. So he cannot tell what the first person voted. Because the first person just gave him the total. And then the second person passed the total, also his total to the third person. The third person cannot tell what the second person voted. Now I want to give you the results of the vote. That's now what I want to give you. Let me stop sharing first so that I can get, oh, yeah, to write. It's okay, I've found it. Now, so the results that we have, the result that I have is 910. No, 920, 929 is the result that I have. That's the total that I have. Just change the color. Now, what my secret number was 910. That means we've the votes cast are 19. Is that okay? 19. Now, so we want to know how many people voted yes, and how many people voted no. Is that okay? That's what I want to use the divisibility test. We have 19 votes. And if you are to vote yes, you are voting 6. Is that okay? So I ask myself, 6 into 19, how many times? And 6 goes into 19 3 times. Is that okay? The remainder is 1. The remainder is 1. So this tells me that 3 people voted yes. Voted yes. This is what it tells me. Then it tells me that one person voted no. Voted no because we casted 1 vote. There's a cast of 1 vote. Is that okay? And then 3 people voted yes. Is that okay? We were 5. We were 5. That means 2 people never voted. So 2 people abstained because we are 5. So you can see what we've used is the knowledge of divisibility. And we've ensured that our voting is secretive. Instead of telling people, raise your hand so that we count you, we count how many people are voting yes and how many people are voting no. You just write a piece of paper, you write a number, a secret number. Is that okay? Then you give the people, and then you tell them, the person wants to vote yes, vote this number. You write this number. If you want to vote no, vote 1. And if you want to abstain, vote 0. And then you can use the divisibility test. Now, so my choice of the numbers is very important. I knew that we were 6, we were 5. So then I decide that if we are 5, if you have to vote yes, then vote yes. Vote 6. Because I wouldn't have said vote 5 if you had to say yes, vote 5. Because what if 5 people vote no? If 5 people vote no, and the people and 1 person votes yes, you will not differentiate between the 5 for no and the 5 for yes. You will not differentiate. So that is so for you to choose that when you're choosing now which numbers to allocate, just choose if you have 5 people, let somebody voting yes use 6 to say yes, and 1 to say no, and then 0 to say that is abstaining. So I think we have seen some application of divisibility test that is in cryptography. Although this is not a very serious application, but when we have friendly committees, we can use such type of voting. I've said friendly because supposing it's not a friendly committee, if the first person that I gave the piece of paper colludes with the 3rd person, they can know what the second person voted. If the first person colludes with the third person, they can know what the second person voted, because the third person will just ask the first person, what was the secret number you received? Then he says the secret number he received. Then he says the vote he casted. Is that okay? If he says the vote he casted, then the third person is able to tell the total he received, how it changed. Because if I gave 910, and then he says I received 910 as the secret, and then I voted 6. And then the third person says I received 916, which means this person abstained. Is that okay? So that means if the committee is not very friendly, there are some people can collude to tell what the other party voted. And by so doing, if maybe they want to cause some harm to that person, then they will do that. Is that okay? So it means it's not very secure way of voting. You cannot, what that means is that it has some insecurities. It has some insecurity, so you cannot depend on it so much as the other types of the other ways of safeguarding in communication in cryptography. So you have other good ways of safeguarding communication in cryptography. So we try to safeguard this one, but we've seen that it's not a very good way of safeguarding. Now, so I want to show another example. Just again for this type of voting, so that there's a mix. Now, let's look at this other example. I want to emphasize on your selection of numbers. Now, assume that we have a committee that has 26 members, and we want to vote for budget just as we've done here. And then the members prefer that their vote should not be known. They want to vote anonymous. Now, so what we do the same way we've done, because there are 26 members. Let's assign them ABC, so that the chair takes the number A, then the last person, number 26th person, takes Z. So the chair will then write a secret number, just the way I did. The chair, let me say the chair writes 9,340 on the piece of paper. Then it passes to the first person. And then he tells the first person and all the members that if you are voting yes, then add 27 to the total you will get. But if you are voting no, add 1. But if you are abstaining, you add a 0 to the total. So the person B will write his sum or her sum to the new piece of paper and take the other piece of paper back to the chairman. Then hands this new piece of paper to person C. Person C also casts his votes and returns, I think it's person B. Person B was supposed to receive the paper from the chairman, which is written this number. Then he's supposed to return that piece of paper. So person B is the one returning this piece of paper to the chairman. Person C also votes. Person D votes. All of them votes up to person Z. And then they give back the chairman also casts his vote. Now, supposing that the total at the end of the day, at the end of that voting exercise, supposing the total goes to 9,858. the chairman will know how many votes were cast. Is that okay? Because the chairman had written this 9,340 secret number. And now, since the total votes are this, the chairman just gets the difference. And the difference will be 518 votes, which were cast. Now, from there were 26 members. There were 26 members, and a yes was 27. So the chairman is able to tell how many people voted yes, because there are 19. Is that okay? There are 19. Then the remainder is 5. That means 5 people voted no. And then, so what total is that? 19 plus 5, that is 24. It means 2 people abstained from voting. So that is the easiest way of applying this divisibility test. You can try it later. But as I've said, that is not a very secure way of voting. If you wanted to safeguard everybody, this is not the best way. Because as we've already indicated, that if 2 people collude, they can know what the middle person voted. Is that okay? Yes, they can tell what that person in the middle voted, and if they were to do anything, that person, then they can do that. Now, so I just wanted us to see that application bit, and then from there, I wanted us to discuss these questions. With this, we've already covered these parts. So I just wanted to find out whether we understood what we covered by answering these questions, either as a group or individual. So after you've done them, we discuss them together. But you begin by, first of all, doing these questions, and then we discuss. So you can do them as a group or as individuals. So what we can do is, maybe we do the first question and then the second question, then we discuss. After that, we progress to the third question and the fourth question, and then again we discuss, and there are several other questions after this. So let's do question 1 and question 2. Yes.
Aside from the security of the method, is it possible to use such divisibility method of determining how many number of people voted for a large number of groups? Let's say 1 million people want to vote in some. Is it practical for such a model, or is it more practical for a small number of people? Because I'm looking at things such as they might be able to tell maybe who voted for them, but now it's a large number of people, a certain number of people.
Yeah, if it's a bigger number, then that method will not work, or it will take a long time to work. It will take a long time. It's just for smaller committees. Smaller committee, for example, you have a committee of 20 people, a committee of 30 people, and you want to do some secret voting so that you want to make decisions on a very key matters, and some people don't want to be known what positions they took. Then that kind of secret voting can be used. But if it's for a bigger group, then it will not work. It will take a longer time.
Then I noticed for voting yes, for example, you always use a number that's 1 member with a number of people. But does it have to be 1 more, just a number higher than the number?
1 more is better. One more is the right one. Just as I explained, for instance, supposing we took 5 and there were 5 of us. Now, if 5 people decide to vote no, and then 1 person votes yes, those are 5-5. This 1 person voted yes, that is a 5. And these 5 other people voted no, that is a 5, because 1, 2, 3, 4, 5. Is that okay? Now, so you not tell Which 5 is for what? Is this 5 for no, or is it for yes? So you're not to be able to tell. That is just one case. But the other cases, where now, you see for this case where the 5, you may not see the impact. For larger numbers now, the impact will be there. Yes.
So my question now was use 6.
Yes.
Yeah. So if we decide to use 7, for example, will it still work the same way?
It will just be like the case of this 7, the case of 5. Like the case of 5, for instance, supposing we choose 7. So supposing 3 people. No.
My question was, you have 5 people who are voting.
Yes.
So for yes, we use 6 to denote that yes, you are voting yes.
Yes.
So in the same case of 5 people, can we use 7 as a representation of voting yes? My question is, does it have to be one more than the total number of people, or it has to be a number higher than the total number of people as a representation of yes?
One more is the best. One more is the best. Every time you choose, if you choose less or if you choose more, there comes a time when you cannot tell which number is for, because I'm subtracting. I'm subtracting here. So it's not easy for me to tell whether this 7 that I'm saying is for no, or whether it is for yes. So it becomes a bit tricky. And when you say just one more, it becomes easier. Yeah. So let's continue doing those questions. So if you are done with the first one, you can come and assist us. Just come and help us here with your workings. Just come and use this. Yes. 5 divide 70. 170. Yeah.
Okay, to show 5 divides on 70 without a remainder, we can confirm it by doing the long division, which is 75.
Was it 170? Was it 71?
I'm not so sure. I think it was 70.
Let's get back and see what it was. It's 170. 170.
Should I just
Yeah, just make it 170. Yes.
to show 5 divides on 70, you can do the long division to prove it. So 5 goes into 17 3 times. Now 15 and then 2 here, and then we drop the 0. Now okay, it's a 0. Now 20 divided by 5 is 4 to give us 20. We have no remainder. So this proves that 5 divides on 70 without a remainder. So yes, it's correct. And then the other one is 126. 14. So we want to show that 14 divides on 26 without a remainder. We're going to use the same long division. So in this case, okay, 14 goes into 26 how many times? 9. So 14 by 9, 14 times 9 gives us 126, and we have no remainder. So this here shows that 14 divides 126 without giving us a remainder by using the long division method. So both are correct.
Okay, so that is okay. That's okay. So what we learned was that what our definition of divisibility, we said that a number A is said to divide C if there exists another number, if there exists another number B, such that C is equals to AB. Is that okay? So in that case, then it means, just as he has said, we say therefore, we say that 5 divides 170, since 170 can be written as 5 times 34. So where if 5 were to be A, then 34 is the B. So this is using the definition of divisibility. And in the second part, as he did, we also say that 14 divides 126, since we can find some number 9 such that this 126 can be written as 14 times 9. So this is how we also show it, by using the definition of divisibility. Now, so we look at the second question. The second question, you said you had done it also. Okay, let's look at it. This is the working for the first question. The second question required us, what is it? It said, use the Euclidean algorithm to compute the GCD of these two numbers. Okay, come and show us how to use the Euclidean algorithm to compute that GCD.
Okay. We're now using the Euclidean algorithm to compute the GCD of these two numbers. Let me write them down. So okay, so the two numbers are 4,115, and the second one is 22,630. Okay, so to use the Euclidean algorithm, we're going to take the two of the larger numbers and then we're going to divide it for 15. Now we want to find the quotient between the two numbers when we're dividing 22,630 with 4,115. So 4,115 will go 5 times, and the remainder is going to be 2,055. And then take for the 4,115, we put it outside, and then we take the remainder of the first equation. So it will go 2 times, and then the remainder is going to be 5. We do repeat the same procedure again, and we can see that here we have no remainder because they are both multiples of 5. So it will go, so 5 will go into 2055, 411 times, and then our remainder is 0. So our GCD here is going to be 5. So the GCD of 4115 22630 is going to be 5 using the Euclidean algorithm.
Okay, that's okay. That's how you find the GCD using the Euclidean algorithm, and we saw how the Euclidean algorithm is very important in cryptography and other areas of mathematics. Now, so let's now do the third question and the fourth question. Then again, we discuss. The third question is that, I think we should just do the third question first of all, then discuss it before we proceed to the fourth question. Wanjiru had said something on our voting that we did. She says that addition of 0 and 1 is this becomes our secret key. It is the n factor on which the algorithm can be decrypted. So if you want to decrypt the algorithm, then that is what you use. She says that that is our private key. That is the first question we were doing. That is on the voting. Okay, are we done with the part A, B, and C? I think you can now just move together. Is that okay? This one's you can just do it direct together. Yes, you want to try? The lady. Come and lead us in part A. The LCM. Hmm? Just the normal method.
So for LCM, we start with the first digit. We have most numbers, so 12 and 30. So we know LCM. We have 12 here and 30 here. We start with the least divisor for both. So 2 here, 6, 15, 2 here, 3. It can't go into 15 without leaving a remainder, so we just write 15. Next we have 3, here it goes once, here 5 times, then we have 5, of course here it's just 1, then here we have 1, so we have 2 times 2 times 3 times 5, which gives us 5 times 3 is 15 times 2, 30 times the other one is 60. And then you're supposed to get the LCM, and then the second part is supposed to compare. Okay, so we also now get the GCD. I used the equation. So we have 30 equals 12 twice plus 6, and then we have 12 equals, okay, 6 twice plus 0, so the last non-zero remainder is 6. So our GCD is 6. So now we have M and N are 12 and 30. LCM is 60, and the GCD is 6.
What is the comparison? What can we say is the relationship between LCM, GCD, and the two numbers? What can we say from the group? Yes. From what she has found, we can see that she has a GCD of 6. She has LCM of 60, LCM of 60, and then you have the two numbers. What can we say is the relationship? Now let's get the product of those two numbers. What's the product of those two numbers? 360. Okay, so what I wanted to say is it true that the product of these two numbers is the same as the LCM times the GCD? Let's just check the product of those two numbers. What's the product of those two numbers? 360. And what is the product of LCM and GCD? 360. So can we confidently say that given A and B, the product of A and B equals to GCD of A and B times LCM of A and B? Can we say that? You can say that.
Yeah.
Let's confirm that using the next question. Yes, just erase this so that we confirm that using the next question. So what you just said, you said that the product given A and B, given A and B, you can say that the product of A and B is equals to LCM of A and B times GCD of A and B. So we just want to confirm this fact using the next example.
Okay, so the next set of numbers is 10 and 20. Here, LCM, computing the LCM, we have 10, then 20, and 2 goes into 10, 5 times into 20, 10 times, then the next one is 2, 5, and then we have 5 going here once and once. So 5 times 2 times 2 gives us 20. So we have the LCM is 20. And then the GCD, I have a question. Here, how do you explain the first place is no remainder? Like now it's just 10. Okay, I know the GCD is 10. Okay, so GCD, we get 10. I have to explain how I get the GCD. Oh, this one is okay. So 10, 20. Here, the smallest is 2, going here 5, and going here 10 times. And then the next one that's common for both is 5, going here once and going here twice. So we have 2 times 5. Sorry. Yeah, 2 times 5, which gives us 10. So we have the LCM as 20, and we have the GCD as 10, and we have the two numbers, M and N, as 10 and 20. So here, when you multiply 10 by 20, you get 200. So those are the two numbers, M and N. And when you multiply the GCD of both numbers, which is 10 and 20, you also get 200. So it's true. Yeah. And the product of the two numbers is equal to the product of the GCD of the two numbers and the LCM of the two numbers. Okay, how do I do this again? Thank you. So the last set of numbers is 60 and 180. LCM again, 60, 180. Two going here, 30, and here 90. Then we have 2, 15, 45, and then we have 3, 5, 15, and then we have 3, giving us, okay, here we just drop the 5, and then here we still have the 5, and then now we have 5, 1, 1, so we take 2 squared times 3 squared times 5. Now this is for the LCM, and the answer is 180. And then now computing for the GCD, as I had done before, 60 and 80. So definitely here 30, here 90, 2 again, 15, 45, 3, 5, 15, and then now 5, 1, 3. So 2 squared times 3 times 5, which gives us 15 times 4, 60. Yeah, so our GCD is 60. So as before, when you multiply the two numbers, 60 by 180, 60 by 180. You get 10,800. So 60 times 180, that's our M and N. You get 10,800. And when you multiply the GCD by the LCM, which is just 60 and 180 again, you get the same number, 10,800. So it proves again that when you multiply two numbers, M and N, you get the same answer as when you multiply the LCM by the GCD.
Now, so that's how you do it. I'll begin by answering a question she asked, how to get GCD using the Euclidean algorithm when the two numbers on division, the first division, the remainder is 0. And the example there was 20 and 10. So the GCD of 20 and 10, how do you find it using the Euclidean algorithm? That was the question. Also, she said that if you take 20 and divide it 10 into that, the remainder is 0. So then she asks, how do you use the Euclidean algorithm? But what is interesting here is that this is the divisor. This is the divisor. This is what is interesting. Is that okay? Now, let me put this on aside and look at another example and see, relate the two examples. Let's look at 5 and 2. We want the GCD. Is that okay? Now, so we normally say 5, 2 goes there twice, and the remainder is 1. Then we say 1 into 2. 1 into 2 twice. 1 into 2 twice, and the remainder is 0. 1 into 2. So this is the divisor. This is the divisor. And this last divisor here, this last divisor that gives us a 0 remainder is the GCD. Is the GCD. I don't know whether you've seen my point. The divisor at that point, when you're getting the remainder to be 0, the divisor at that point is the GCD. I don't know whether you're seeing that point. So that I've used this example. And this example I've shown you that at this stage, we are saying this, how many times does this 1 go into 2? And 1 goes into this 2 twice. So at this point, 1 is the divisor. at the point when you are getting the remainder to be 0, 1 is the divisor. This one is the GCD. Let me look at another example again. Let me look at 16 and 3. 16 and 3. And this is another example. And we say 3 goes there 5 times. 5 times, is that okay? And the remainder is 1. Let me take another, this example is like the first one. Let's just complete it, but then I pick another one. Then we say this one into this 3. This one into this 3 to go there 1, go there 3 times, and the remainder is 0. So the divisor at the point when the remainder is 0 is the GCD. Let me take now a type, one that does not give us a GCD of 1. Let me talk of 8 and 4. What for? 16 and what? We talk of 24 and 9. Let me talk of 24 and 9. We talk of 24 and 9. Is that okay? So we say 9 into 24, how many times? Twice. And the remainder is 6. Is that okay? 6 into 9. 6 into 9 once. And the remainder is what? 3. 3 into 6. 3 into 6 twice. And the remainder is 0. So the divisor at this point, it's 3 we are dividing into 6. So we're asking ourselves 3 into 6, how many times? So 3 is the divisor at this point when the remainder is 0. So 3 becomes the GCD. So now I come back to our first question that she was asking. How do you use the Euclidean algorithm when on first division, the remainder is 0? So it's the same logic that the number that is dividing is the GCD. So in the last example she has done was 60 and 20. Was it 60 and 20? Was it? It was 180 and 60. 180 and 60. Yeah, she was finding the GCD of 180 and 60. And we are using the Euclidean algorithm. We just ask ourselves 60 into 180. 60 into 180, how many times? And the remainder is 0. So the divisor at that point, when you are getting the remainder of 0, becomes the GCD. Is that okay? So the GCD, therefore, is 60. The divisor at the point when the remainder is 0 is the GCD. So I wanted to begin with that because she asked that question while she was responding to the questions. Now let's look at the last part of that question 3. The last part of that question 3 here. And the last part says, use your result in B to compute the LCM. So what is the result that we found in B? The result we found in B is that given two numbers M and N, given two numbers M and N, we discovered that the product of these two numbers, is the same as the LCM of these two numbers times the GCD of these two numbers. That's the product, that's the result that we found. So it's this result that they're asking us to use to compute the LCM of these two. So what this then means, how do you find the LCM? You find the LCM by dividing by GCD on both sides. When you divide by GCD on both sides, you find that the LCM therefore will be given by the product of these two numbers divided by the GCD of these two numbers. So that is what they want us to do. So in other words, they just want us to find the GCD and then the product and get the LCM. So let's go straight to find the GCD. It is 816 and 936. The GCD of 816 and 936. So you have 936. The other one is 8 what? 816 goes there once. 816. What's the remainder? 816 from 936, 20, 120. Okay, 120. 120 into 816. How many times? 6 times. And the remainder? 96. 96 into 120 once. And the remainder? 24. 24 into 96, 4 times. And the remainder? So we say this is divisor here. This divisor becomes a GCD. Is that okay? So the GCD therefore is what? 24. What we want is the LCM. We found that the LCM is the same as the product of the two numbers divided by the GCD of the two numbers. The product of the two numbers are 936 and 816. And the GCD is 24. So we can just use a calculator here. What do you get? That one, 8. This is the LCM. So that's how you use that knowledge to find the LCM of the two numbers. Now, so we do one question, then we have some break after the next question. So the next question is, find a solution in integers for the following equation. Now this one I want you to do it. They want us to find the value of x and y such that 18,107 times x plus 3,292y will give us the GCD of these two numbers. So we come and do it. Yeah. There's enough space here. But
So let me write first the equation is looking at. So at this point, we're going to use the extended Euclidean algorithm so that you can be able to find the value x and y in that. When we multiply x with x and y with each number, each subsequent number, we're going to find the GCD between the two numbers. So we use the extended Euclidean algorithm. So between the two numbers, so the number is 18107. 3292 is going to 1817 5 times, and the remainder is going to be 1647. Then we do it another time. Now for 3292 and 1647, it's going to be once, and then the remainder is going to be 1645. Then 1647. 1645 is going to go into 1647 once, and then the remainder is going to be 2. Then 1645, 2 is going into 1645 822 times, and then you have a remainder of 1. Then now 2, where 1 is going to 2 1 times, where 2 times 1 is equals to 2, and then our remainder is 0 basically. So I think our remainder is going to be 1. Yes, the GCD is going to be 1. Sorry. So once we have our GCD, we can now use I want to call it, we are going to propagate backwards using our 1. So we are going to make 1 okay, I have to use this one. We're going to make 1 the subject of the equation. So 1 is equals to 1645 minus 2822. And then we're going to substitute these two using this part of the equation. So I'm talking about these two here. We're going to substitute it using this part of the equation. So it's going to be 1 is equals to 1645 minus 1647 minus 1645 1, then 822 times, and then we're going to open the equation. 1645 is equals to 1647 822, and then plus 1645 822. Okay, and then we collect the like terms. 1645 plus the 822 is going to be 823 minus 1647 822. Okay, now we're going to substitute the 1645 here using this part of the equation. Then we're going to have 3292 minus 1647 823 times, and then minus 1647 822. Now we open up the equation. 3292 823 minus 1647 823. Oh, I'm sorry about the handwriting, but I think we can just continue. And then 1647 822. Let me try and write something which can be read. Okay, now we take the like terms. It's going to be 3292 823, and then minus 1647 Now 820, 23, all together. We're going to get 1645. Okay, now we're going to substitute the 1647 part of the equation using this part. Okay, first let's refactor this equation to look something like 823 1647 1645. Now we're going to substitute the 1647, this one, using this part of the equation. So it's going to look something like 3292823 plus 18107 3292. Then we multiply it by negative. Yes. Then we open up the equation. Negative 8225. Now we collect the like terms together. So I think this one is going to be a positive. I'm not so sure about it, but I assume it's going to be positive. Is it going to be a positive? Because at the end of the day, I'm still not multiplying them together, so I'm not so sure about it. We have a positive here and a positive here. I'm trying to put a positive in front of it, but I'm still not getting the we have negative 3292, and then we have the brackets, the negative 8225. I was thinking about, I'm not so sure if it's going to work. Maybe if we put a positive in front of it, and then we have all positives. Or we can make it positive here.
Okay.
It's going to
Yeah,
work.
I'm trying to follow. How do you come to negative 8225?
I multiplied negative 1645 with 5. Top here.
Just maintain, if it's a negative, just maintain a negative.
So we can use this part. We don't have to do what only here.
Yeah, just collect like terms.
Okay. So we're going to collect this part together with this part here. Now 3292, we're going to take the negative,
That 3292, the one who just put the bracket now, is it negative?
yes, it's negative. And also the part inside it is negative.
That becomes positive.
So I was asking if you can put a positive.
Yeah. If it's a negative, then you get.
So we can use this part of the equation, the last one. Now we add them together because we are adding. So we have 3292 9048 plus 1817645. Okay, so maybe we can use our calculators to see if the numbers we found here are going to equal 1 once we multiply them. Yes, so the value of x is going to be negative 1645. The value of y is going to be 9048.
Okay. Any question on what he has done? Began by finding the GCD using the Euclidean algorithm. And then you used the extended Euclidean algorithm to find, to write the GCD as a linear combination of the two numbers. And he has tried to confirm that the two numbers given are correct. Is there any question? Now, yeah, what he has done is okay. So if there's no question, I think we can have a break. Then we come back for the other questions. Just a break of about 10 minutes.
Using the squaring formula. So we're going to do 7 to the power of 1, the 737, which is going to be 7. And then 7 to the power of 2 is going to be 49. 7 to the power of 4 is going to be 49 times 49, 2401. And then 7 to the power of 8 is going to be, I think I'm going to need a distributive assistance here. 8, so 2401 squared. Yes. Seven three seven. Okay, so it this one
What's the use of the letter? You just say, use it.
I don't want to use the word
Finally, display the terms. What happens when you change that to minus? Just change this to minus. And then times 580. The easiest way after you've done that, you can you found to be 780.50. So just subtract 780. Subtract 780. You remove that whole number. The answer that you get now multiplied by the moduli, which is 73887. $29.41. What are you getting? When you square 2,401, then divide by 7,387. The remainder, or you're still 7 raised to 4. Okay.
I think yes, I think this is the last digit you need, because if you multiply it by 2, it's going to be greater than this one. So we need to find its multiple. So we find how many times we can represent the number 7387 using the squares of 2. So it's going to be, okay, it's going to be 1486, then 2048, and then I'm going to add it below here, and then 1024, yes, 1024. Then let's try adding. If we add 12, we're going to exceed it. So we add a lower number, probably let's try to 56. 56 is going to exceed it. 120. Yes, let's add 128. And then let's try 64. Yes, 64 is within our bounds. We think that 2, no, 2 won't work. Let's try 16. Okay. Then let's try 8. And then let's try 2 and 1. I think it's going to add up to 737. Let's confirm it. Now let's substitute the numbers we found. Okay, so for for 1486, the mode was 2227. Okay, first we have to remember that we are doing it as a multiple of 7. In that we had 7387. It's going to be 7 in the power of 1486 times 7 to the power of 2048 up until we reach 7 to the power of 1. So this remainders we're finding, we have to divide. We have to multiply them. We won't be adding them as we are showing here because of the indices, the rule of indices. So 2227 times 3713 times 1424 is 4992 times 128, 2448 times 64, 6262 times 16, 6691 times 82941, then for 2, 49, then for 1, 47. So I think a good idea will be pairing them, then finding the mode of each, then going down each step on the one. So we try 2227 times 3713 mode 7387. We're going to, oh, okay, I've noticed a problem. I think we are going to do 86, not 87. So we have to remove this one here. So we won't be multiplying by 7. I think you have noted that error because we're doing the power of 7386, not 7387. So if we're doing for 7386, the one here is going to give us a wrong answer. So we want to be using term 7 here. Okay, I think that's an error. Okay. So this proceed. Yes, it's adding up. So yes. So we're going to pair 2 7 times 3713 mode 787. 7387. So for the first two values, we're going to find that our mode is going to be 2798 times, and then we proceed to do for 4992 times 2448 737. Okay, so 4992 times 2448 mode 737 is going to give us 2318. Now we proceed with 6262 times 6691 mode 737. Our value is going to be 7,365, and then 2941 times 49 mod 737. 2941 times 49. So the last part is going to be 3756. Yes. Now we are going to take this part, we do it mode 737, and then this part together, the second part. 2798 times 2318. 737. So the first part we're going to find is going to be equal to 7365. Then we do the remaining part. The second part is going to be these two. I think we're going to use a simpler method where we're going to take 7365 minus 737, and then we're going to divide it to multiply by two answers. So 7365 minus 7387 going to give us, okay, no, because 7365 7387, it's going to give us negative 22. And then the second part, 6012 minus 7387 is going to give us negative 1375. Then we multiply the two. 375. And then when we multiply 1375 times 22, we find it's going to be 30,250. And then we're going to find mod 7387. So I think this is going to give us our answer. So our answer is going to be 702. If someone can confirm if our answer is right, it's correct. So our answer is correct.
we know that by Fermat's little theorem, we know that if P is prime, then A raised to P minus 1 is congruent to 1 mod P. That is, if P is prime and if P cannot divide A, then A raised to P minus 1 should be congruent to 1 mod P. In this case, you can see that the power we have is this number minus 1. This number minus 1. And this number cannot divide 7. But the answer that we get is 7 or 2. It's not the same as 7, it's not the same as 1. If it would have been 1, we would have said that this P is likely to be prime. But in this case, since it's not equal to 1, we confidently say that this number is not prime, it's not a prime number. So that is one way we can test if a number is prime, by using Fermat's little theorem. Now, so I had asked whether we can reduce the number of steps. And we had discussed that earlier in one of our classes. We had said we can use binary numbers. So you change the power to binary. And in this case, when the number was changed to binary, what did we get? So this, what did you get? You have that number. We had changed this power to binary. We had found some, the one you did. Yes. So 786 to binary was 1110011. How many ones? After the 2 zeros, how many ones? 5 ones. Then okay. It was somewhere. It was 1. It's here. This one. So those are 3 ones, 0, 0, 2 ones. Just write it here. Two ones and then 2 zeros. Huh? It's okay. So this is the number in binary. So, and there's something, while he was doing this question, there's something he did here. He was finding out, trying to find out which numbers we would add to give us the exponent at this part. So he said to get this exponent 7386, he was going to add 4096, then add that, then add this. So he chose from this, among these, the ones that had these powers, from among these. So the number of steps that I'm looking at reducing are those which we are not using here. The ones we are not using here are the ones I want to eliminate in this squarely. For instance, this was not, okay, this was used. Which one? This one was used. That is 4096. Then 2048 was used. 1024 was used. 128 was used. Then 64, 16, 64, 16, 8, and 2. So then I'm thinking of, if we were to make it shorter, then it means we have to try and see how we can get rid of this. How we can get rid of this, the ones that were not used, so that we are only working with the ones that we know we are going to use. So how do we know we are going to use those ones? We change the number to binary the way she had changed it. So the ones that have a 1, those are the ones which were used. So this one is raised to power 1. When you raise to power 2, this is what you get. When you raise to power 4, this is what you get. When you raise to power 8, when you raise to power 16, power 32, power 64, power 128, and so on as we go this way. So you can see when it is power 1, where there's a 0, that number was not used. When the power is 1, it was not used. When the power is 4, it was not used. So you can just verify that they were not used. So when the power is 1, it was not used. When the power is 4, it was not used. And when the power is 32, again, it was not used. When the power is 32, let's just go back to the binary. Yes, when the power is 32, it was not. So where there's a 0 on the binary number, you don't require that multiplication because it will not be used. Is that okay? So the easiest way, therefore, once you have changed this number to binary, we say you take a raised to 2, then raised to I. A raised to 2 raised to I, where I is from 0, 1, 2, and so on. So when I is 0, what you get is a raised to 2 raised to 0, which is same as a raised to 1, which is just a. But that one was not used. When I is 0 was not used. So what we used was when I is 1 was used. So that means we shall use a to I is 1. So let me write it here. A raised to 2 raised to 1 will be used. A raised to 2, this is 0, 1, 2. This will not be used. 0, 1, 2. Then the third one here will be used when I is 3. When I is 3 is used. Is that okay? When I is 3, when I is 4 was also used. When I is 4 is used. The other one that is used is when I is 5. When I is 5. Is it that one? This is 0, 1, 2, 3, 4. When I is 5, this one. That one was not used. When I is 6, when I is 6, it was used. When I is 7, so this is a raised to 2 raised to 7. Is that okay? This is 8, 9. When the I is 10, when I is 11 was also used. Then when I is 12, when I is 12. So that means we will have reduced the steps. How many times? So we're only dealing with this number 1, 2, 3, 4, 5, 6, 7, 8. We're only doing it 8 times. Then get rid of the other steps. Is that okay? Now, so how do you multiply therefore? How do you multiply if you have to reduce the steps? We know when I is 0, that is, let me take, for instance, the number we have was 7 raised to 1. Was it 7? The base was what? The base was 7, yes. The base was 7. So 7 raised to 1. 7 raised to 1, this one was not used, but we must have it, so that we can use it to get the rest. That one was not used because it gives us a. Now, what we used was 7 raised to 2. Is that okay? 7 raised to 2. So we must get that. Then, so this is 7 raised to 2. 2 raised to 1 is 2. Then 2 raised to 3. So we must find this, we must find this, we must find this, then come and find 7 raised to 2 raised to 4, that is 16. Is that okay? Yes. Then 2 raised to 6. 2 raised to 6. Is it 64? 64. And then 2 raised to 7. 120? 128. So you must find what this is, find this, what this is. And then 7 raised to 10. 7, no, 2 raised to 10. What is that? 1024. Then I must also find 7 raised to 11, no, 2 raised to 11. Which is 2048. And that is what he used. That's what he used. This one was, what was the last one? This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Then 2 raised to 12. 2 raised to 12 is the last one. 496. So these are the only ones which are required to do this question. And we are doing it mod. We are doing it mod 7387. Mod 7387. So this one, you need 7. What about this one? It is 49. This is 49. Is that okay? What about this one? This one you can do it easily because you don't have 7 raised to 4. If you would have been having 7 raised to 4, we would have squared it. but we want to reduce our working, so we don't have it. So, but what we have is 7 raised to 2. Is that okay? And we know that the 7 raised to 8, the same as 7 raised to 2 plus 2, how many times? Plus 2 plus 2. Which is the same as what? 49 times 49 times 49 times 49. Is that okay? Mod, remember the mod, And so you just, let's do this, just multiply this. Let's multiply this and do it mod 70 what? 470. The mod was, yes, just multiply that and do it that mod. So we just trying to reduce the steps that we're supposed to, or we have fewer steps. And it's easy even to write an algorithm with these steps now. So that is 49 times 49. That is 49 4 times mod. Remember the mod. Now, if it's bigger than, if it gives infinity or math error, then you work with the 2 first, you pair them. Let's just do that before, then we'll stop. Just do this one, then you can do the rest. That'll be 49 times 49 times 49 times 49. That gives me 5 million, and that divided by, our mod is what? 7387. I get 780. I get 780 on division. So what is the remainder? The remainder is 2941. Let us see what we had gotten earlier for that same number. 7 raised to 8. We got 2941. 2941. And that is what you've gotten. So this one, now the next one is easier. The next one, this is square of this. You just square this. Mod, that mod, is that okay? And this one is not a square of this. So now think of how do you get 64 from what you have. You have this, you have 8, you have 2, and that. How do you get 64 from that? Is that okay? And do the rest that way. Okay, so I think we can stop at that. Okay.